At the edge of our solar system, where the light of the sun falls like a distant glow through the darkness of space, a mighty planet orbits alone. A place so cold and so far away that it hardly plays a role in most people's imaginations, yet it is a fascinating part of our cosmic neighborhood. A blue giant with an eventful history and many unsolved mysteries. Its name, Neptune. Neptune is the 8th and outermost planet in our solar system, not counting Pluto, which was officially downgraded to a dwarf planet in 2006. It is located at an average distance of almost 4.5 billion kilometers from the Sun, a place beyond the so-called frost line, where ice and gases could condense into enormous celestial bodies. It is so far away that a ray of light from the Sun takes over 4 hours to reach Neptune. A year on this blue gas giant lasts 165 Earth years. Since its discovery, the planet has completed just one full orbit around the Sun, a cosmic snail's pace. And this discovery was one of the most spectacular in the history of astronomy. Neptune was the first planet to be found not by optical methods, but by pure mathematics. In the early 19th century, astronomers noticed that the planet Uranus was behaving strangely in its orbit. Its position in the sky deviated minimally but measurably from the calculated values. Two scientists, John Couch-Adams in England and Aubin Leverrier in France, independently suspected that a previously unknown celestial body must be influencing Uranus with its gravity. Leverrier sent his calculations to the Berlin Observatory, and there on September 23, 1846, German astronomer Johann Gottfried Galle pointed his telescope at the calculated position, and then he saw it. A small bluish point of light in the sky, but undoubtedly a planet. A scientific sensation, a planet predicted by mathematics. The discovery was a triumph for celestial mechanics and proof of how deeply the laws of nature and the cosmos were already understood, at least in their basic principles. Neptune was soon named after the Roman god of the sea, an allusion to its deep blue color, which was already visible with the instruments of the time. But despite this promising discovery, Neptune remained a distant mystery for a long time. The telescopes of the 19th and early 20th centuries showed little more than a smooth, featureless sphere, too far away, too faint, too small in the sky. That didn't change until 143 years later. In the summer of 1989, NASA's Voyager 2 probe flew past Neptune, a final bonus stop on its journey through the outer solar system. It was a flyby with only a few hours of close contact, but those hours were enough to fundamentally change our image of Neptune. The probe transmitted detailed images of a deep blue world crisscrossed by huge storm areas, white methane clouds, and the so-called Great Dark Spot, a gigantic hurricane as large as Earth, which later disappeared and cannot be found today. We saw a planet with tremendous dynamics despite its location in the icy darkness. Neptune's atmosphere consists mainly of hydrogen, helium, and methane. The latter is responsible for its striking blue color, as methane absorbs red light and only reflects blue. But what really makes Neptune special is its weather activity. It is home to the fastest storms in the entire solar system, with wind speeds of up to 2,100 kilometers per hour. In comparison, a hurricane on Earth seems like a gentle breeze. How is this possible, so far away from the Sun, with so little external energy input? This question has not yet been conclusively answered, but the planet's internal heat probably plays a role. Neptune radiates more than twice as much energy as it receives from the Sun. This is an indication of a hot, active core hidden beneath dense gas shells. Its magnetosphere is also a mystery. Neptune's magnetic field is strong but strangely inclined at about 47 degrees to the axis of rotation, and also significantly offset from the center of the planet. This is a phenomenon that we have not yet observed in this form on any other planet. In addition to the planet itself, Voyager 2 also revealed an unexpectedly complex lunar system led by Triton, Neptune's largest moon. It moves in a retrograde orbit, i.e. against the direction of the planet's rotation. This is a sure sign that it did not originate with the planet, but was captured later. It is probably a former celestial body from the Kuiper belt, a former companion of Pluto. Triton is also geologically active, with evidence of cryovolcanism. Icy geysers eject frozen material from the interior into space. Despite these exciting findings, there has been only one visit to date. Since Voyager 2, no space probe has ever examined Neptune up close again. No orbital mission, no landing on a moon. The last true planet in our solar system remains largely unknown territory to this day. Why? Quite simply because it is enormously complex and expensive to get there, even Voyager 2. With ideal gravitational assists from Jupiter and Saturn, took 12 years to reach Neptune. A modern mission there would require decades of planning, billions in funding, and a lot of patience. And yet the scientific treasures that await out there could be groundbreaking. Neptune is not just a planet, it is an archive of the early solar system. It is a window into the world of ice giants, which are also very common in other star systems. Those who understand Neptune may also understand other planetary systems, and thus our own better. Thus begins our journey into the icy storms, mysterious moons, and unexplored depths of a planet we know little about, but may soon understand better. Neptune sounds like depth, darkness, a place beyond the known, and that is exactly what it is. A giant that defies our imagination, too distant, too extreme, too mysterious. And yet, or perhaps precisely because of this, it is a fascinating example of the tremendous forces that are still at work even at the icy edges of our solar system. Neptune belongs to the class of so-called ice giants. Together with its neighbor Uranus, this distinguishes it from Jupiter and Saturn, which are considered ordinary gas giants. The difference lies mainly in the interior. While Jupiter and Saturn consist largely of hydrogen and helium, Neptune contains significantly larger proportions of heavier elements, especially water, ammonia, and methane. These substances are mostly frozen at the low temperatures far out in the solar system, hence the term ice giants. But of course, Neptune is not a lump of ice. The temperatures and pressures inside are so high that exotic conditions form there that we do not know on Earth. But before we look inside, let's stay briefly on the surface, or rather in the upper layers of the atmosphere. Neptune's atmosphere is a roaring ocean of gas, dominated by hydrogen, helium, and about 2% methane. It is this methane that gives Neptune its striking deep blue color. It absorbs the red portion of sunlight and reflects the blue light. However, the exact shade is probably influenced by other, as yet unknown molecules. Uranus contains similar amounts of methane but appears much paler. The real fascination, however, begins beneath the surface in the dynamics of the atmosphere. Although Neptune is so far away from the Sun and receives only a fraction of its heat, it is anything but calm. On the contrary, Neptune has the most extreme weather dynamics in the entire solar system. Winds rage there at speeds of up to 2,100 kilometers per hour, faster than the speed of sound within Earth's atmosphere. By comparison, the strongest wind ever measured on Earth outside of a tornado was around 400 kilometers per hour, which is already considered a hurricane of the highest category. Neptune is therefore home to conditions that defy imagination. The atmosphere rotates around the planet in huge bands, similar to Jupiter, but at a much faster pace and with much stronger turbulence. In 1989, the Voyager 2 space probe discovered the so-called Great Dark Spot, a gigantic storm system similar to the Great Red Spot on Jupiter, only darker and faster. It was about the size of Earth and traveled across the planet in a matter of days. But when the Hubble Space Telescope looked again a few years later, the spot had disappeared. A few years after that, a new storm formed in a different location. Neptune's weather is not only violent, it is dynamic, unpredictable, and constantly changing. But where does all this energy come from? It's not the sun. because it's much too far away. Neptune receives only about 1,000th of the solar radiation that reaches Earth. Nevertheless, the planet emits more than twice as much energy as it receives. This excess heat probably comes from within, either from residual heat from the planet's formation or from slow convection processes in its interior. No one knows for sure yet, and this interior is probably as fascinating as it is unreachable. Beneath the turbulent atmosphere begins the so-called mantle, a huge layer of hot, dense ice consisting of water, ammonia, and methane in an exotic state somewhere between liquid and gas. Scientists suspect that this mantle may even contain a special form of water known as superionic ice. The hydrogen ions move freely through a lattice of oxygen atoms, a kind of electrical conductor under enormous pressure and at extreme temperatures. This layer could be crucial to the unusual shape of the magnetic field, because that too is a mystery. Neptune's magnetic field is strong, but massively tilted about 47 degrees to the axis of rotation, and also not symmetrical, but offset from the center of the planet. It is a chaotic magnetic field that differs greatly from the fields of other planets. The cause of this is probably the electrically conductive layer in the interior, but so far there are only theoretical models. The core of the planet, if it exists in a clearly definable form at all, probably consists of rock and metal. However, due to the enormous pressure at a depth of over 10,000 kilometers, even the hardest material there is likely to be extremely compressed. We are talking about pressures that are millions of times higher than on the Earth's surface. What really happens down there is still a matter of speculation, and yet it is precisely this structure that is probably crucial to understanding the planet, not only in our solar system, but also far beyond. In recent years, astronomers have discovered thousands of so-called exoplanets, many of which have similar sizes and masses to Uranus or Neptune. These classes of planets, larger than Earth but smaller than Jupiter, seem to be extremely common in the universe. Neptune is therefore not a special case, but a cosmic archetype. If we want to know how these ice giants function in the vastness of the galaxy, we need to understand Neptune, its composition, its internal structure, its storms, its heat sources. It is a natural laboratory for extreme physics, a place where matter exists in forms that we on Earth can only imagine in particle accelerators or simulations. But so far, our view of Neptune has been only a brief one. Voyager 2 whizzed past in a few hours, took a few pictures, collected data, and disappeared. Everything we know since then is based on remote observation and speculation. Telescopes such as Hubble or the James Webb Telescope provide new insights, but a real visit is still lacking. The blue giant thus remains one of the greatest unsolved mysteries of our solar system. A planet full of power, dynamism, and mystery, a place that shows us that even at the greatest distance beyond visible light, the game of physics rages in the cosmos, just in a completely different form. When we think of a planet, we often think only of the planet itself, its surface, its atmosphere, perhaps its seasons or its rotation. But a planet is more than just a single celestial body, it is a system. And in the case of Neptune, it is worth taking a closer look at what surrounds it, at its moons, and at a little-known phenomenon, its rings. Because Neptune is not alone. According to current knowledge, it has 16 known moons. And at the head of this family is a fascinating, enigmatic object, Triton. Triton is Neptune's largest moon and accounts for over 99% of the total lunar mass of the system. But it is not only its size that makes it extraordinary, it is its origin, its orbit, and its internal dynamics that make it one of the most exciting objects in the entire solar system. Triton is an outsider. Unlike most moons, it does not move in the same direction as Neptune rotates. Instead, it orbits its planet retrograde, i.e., in the opposite direction to Neptune's rotation. A retrograde, slightly inclined orbit is a strong indication that Triton did not form together with Neptune, but was captured later. It was probably once an independent celestial body in the Kuiper Belt, the zone of icy objects beyond the planets. A lost dwarf planet captured by Neptune's powerful gravity, a cosmic immigrant that never quite adapted to its new home. But that's not all. Triton is also active. During its flyby in 1989, Voyager 2 discovered geysers of frozen nitrogen shooting several kilometers high into the atmosphere, a clear sign of cryovolcanism, i.e., geological activity with frozen substances instead of hot magma. This makes Triton one of the few known objects in the solar system with proven geological activity, alongside Jupiter's moon Io, Saturn's moon Enceladus, and a few other satellites. This is astonishing, especially since Triton is so far away from the Sun. Its surface is bitterly cold, around minus 235 degrees Celsius, and yet something is happening inside. Possibly due to tidal forces, i.e., gravitational stresses caused by its slightly elliptical orbit, or due to the slow decay of radioactive elements inside, or both. There are even theories that there could be an underground ocean of liquid water beneath Triton's icy crust, similar to the moon's Europa or Enceladus. If this is true, Triton would not only be a geological wonder, but also a potential candidate for extraterrestrial life deep beneath the ice, far from the Sun, in complete darkness. In addition to Triton, Neptune has a whole series of smaller moons, many of which are little more than captured chunks of rock. There is Nereid, for example, one of the most remote moons in the solar system, with an extremely eccentric orbit, or Proteus, Neptune's second largest moon, a misshapen rock, barely round, riddled with craters. And then there are tiny moons such as Despina, Galatea, Larissa, and Naiad. Many of them orbit close to Neptune's clouds and are probably remnants of earlier collisions or destroyed moons. This inner region is not only full of moons, it is also crisscrossed by a ring system that is often overlooked because Neptune, like Saturn, has rings. However, they are much weaker, much darker, and harder to see. For a long time, their existence was only suspected based on star occultations. It was Voyager 2 that finally provided definitive proof. Neptune's rings consist mainly of dark dust and rock, presumably material released during collisions between moons. There are 5 main rings, the best known of which are called Adam's Ring and Leverrier Ring, named after the 2 astronomers who independently predicted Neptune's existence. A beautiful tribute in the form of dust bands orbiting their planet. A special curiosity are the ring clumps, lumpy condensations in Adam's ring that look like glowing knots called arcs. They bear names such as liberté, égalité, fraternité, inspired by the ideals of the French Revolution. Why these arcs remain in place instead of spreading out evenly is not yet fully understood. It is possible that small moons, such as Galatea, stabilize these structures through their gravity, a kind of cosmic resonance. Overall, Neptune's rings appear much younger and more unstable than Saturn's. It is believed that they are not very old, perhaps only a few million years. It is quite possible that they consist of the debris of a formerly larger moon that was shattered by a collision. If this is true, we are currently witnessing the intermediate state of a slowly disintegrating ring system that could eventually dissolve or transform into new moons. And that is precisely the beauty of Neptune's family. It is dynamic, unstable, and in a state of flux. A mini cosmos of moons, dust, and gravity that gives us a deep insight into the chaotic processes of the solar system. Neptune's moons and rings tell a story of creation, destruction, and change, of captured celestial bodies and broken moons, of geysers of frozen nitrogen and dark dust that envelops the planet like a shadow. And all of this takes place in a region that we have only visited for a few hours, once in 1989. Since then, silence. Yet these moons could be crucial to learning more about the early days of the solar system and the conditions under which life could arise. Triton in particular is therefore a candidate for future missions. NASA and ESA have been discussing a return to the Neptune system for some time with probes such as the planned Trident mission, which could study Triton in detail, because if there is life out there somewhere, it may be exactly where we least expect it. Not under the light of the sun, but under a shell of ice, not on a planet, but on a remote moon in eternal darkness. Since Voyager 2 flew past Neptune in 1989, things have been quiet around the planet. No space probe has visited the distant ice giant since then, no new mission has set out on the long journey, and no camera has documented its rings, storms, or moons up close. The last chapter of active Neptune research is thus more than 3 decades behind us, an eternity in space travel. And yet, the desire to return there is greater than ever, because Neptune asked us more questions than it answered last time. Its interior, its energy sources, its extreme winds, its strange magnetic field, its dark rings, all of this remains a mystery. And then there is Triton, this active retrograde moon with a possible underground ocean. The good news is that science is working on a return. Several concepts are in the planning stage, some are ambitious visions, others are already close to becoming reality. 3 of these missions are particularly exciting because they pursue different goals but complement each other wonderfully: Trident, Neptune Odyssey, and the Triton Hopper. Let's start with Trident, a NASA mission proposed as part of the Discovery program. Trident is, if you will, the most pragmatic plan. A slim space probe, no orbiter, no landing, but a targeted flyby of Neptune's moon Triton with a high-resolution camera, magnetometer, and other scientific instruments. The focus is clearly on this particular moon. Why Triton? Because it combines so many characteristics that fascinate researchers. Retrograde orbits, geological activity, a possible underground water ocean system, and all this at a distance where you wouldn't actually expect it. Triton is therefore a strong candidate for extraterrestrial life, provided there is an ocean beneath the ice shell that is powered by chemical reactions. Trident could find out exactly that. However, with a flight time of around 13 years, this probe would not arrive until the 2030s or even the 2040s, depending on when it is launched. The flyby of Triton is to take place at an altitude of only about 1,000 kilometers, closer than Voyager 2 and with state-of-the-art camera technology. The goal is to map the surface, study geysers, analyze the magnetic field, and if possible, find evidence of an ocean. Even if Trident is only a flyby, it would be a huge leap forward and send an important signal: we are returning. While Trident would be a targeted short visit, the Neptune Odyssey concept goes much further. This is a proposed large-scale mission, an orbiter that would accompany Neptune for many years. Planned and designed by the Applied Physics Laboratory in the United States, Odyssey is one of the most ambitious missions ever conceived for the outer planets. The goal is to study not only Triton but the entire Neptune, including its rings, atmosphere, magnetic field, and moons, up close and over many years. A true long-term project comparable to the Cassini mission to Saturn. Odyssey will not only serve as an orbiter, but will also carry an atmospheric probe that will dive into Neptune's dense, stormy gas layers. This probe would provide the first direct data from the atmosphere of an ice giant, including temperature, pressure, composition, and chemical processes. The ring-shaped dust bands, the strange magnetic properties, and the internal heat source of Neptune could finally be understood with such a mission. In addition, detailed observations of all moons would be possible, including many that are currently little more than points of light in the Voyager data. But Odyssey, as the name suggests, is not a quick mission. The concept envisages a launch between 2030 and 2035, with arrival in the 2050s. Such a journey is long, expensive, and technically extremely challenging, but it would be the scientific accolade for the exploration of the outer planets. Odyssey has not yet been officially approved, but it is considered one of the favorites for NASA's major planetary science missions in the coming decades. And then there is another concept that sounds almost like science fiction: the Triton Hopper. This is a mobile lander that does not stay in one place, but moves around by jumping. That's right, the Hopper would hop from place to place multiple times to explore different regions of Triton's surface. The Hopper would use nitrogen ice from Triton's surface as fuel, converting the local environment into energy. Heating this ice would create a jet of gas that would catapult the Hopper into the air. This would enable it to jump several dozen times across Triton, covering relatively long distances. The concept was researched in the second stage of development as part of NASA's NIAC program. It is technically ambitious, but theoretically feasible, and it would make it possible to explore not just one point, but entire landscapes on Triton, including cryogeysers, trenches, and icy plains. The Triton Hopper is still in the very early stages of development, but it shows how much creative potential there is in exploring this distant world. In addition to these three main concepts, there are other ideas such as the Chinese Shenzhou mission, which plans to fly past Neptune and Triton in 2038, or the ESA-NASA concept OSS Outer Solar System mission, which is intended to be a combination of Neptune research and fundamental physics, and even dual flight missions to Uranus and Neptune such as Odinus have been considered, but much of this is still very vague. Neptune is more than just a distant point on astronomical maps. It is a symbol of what we do not yet know, of the unknown, of what lies beyond the frontier. When we look up at the sky, we see stars, planets, points of light, but behind these points of light lie worlds, oceans of gas, storms that have been raging for centuries, moons where frozen geysers shoot kilometers high into the sky, and perhaps beneath kilometers of ice, even oceans where life could have developed. Neptune stands for everything that we humans have not yet discovered, but could discover. It reminds us that science is more than knowledge, it is longing. The longing to understand, to comprehend, to travel with our thoughts, with telescopes, with space probes. Our space probes are tiny compared to the worlds they visit, and yet they are ambassadors of a spirit greater than any machine. The human spirit of discovery, the desire to cross boundaries, not out of pure necessity, but out of pure curiosity. Neptune is the last great promise of our solar system, a planet that gave us only a fleeting glimpse upon first contact and now waits for us to return. What will we find there? Scientific discoveries without a doubt, but perhaps something deeper as well, a reminder of who we are and what we are capable of when we set out on a journey. The journey to Neptune is long, but it is worth it, because out there, it is not just a planet that awaits us, but the next chapter in our own history.